Hello everyone. Welcome to the series of lectures on the course Calculus and Numerical Methods. In this video, I'll be talking about some applications of Archimedean property. Okay, so let's recall first the Archimedean property that I discussed in the last video. So these were the two Archimedean properties, two forms of Archimedean properties that we saw in the last video. Okay, the first one, AP1, said the set of natural numbers is not bounded above in R. Okay, and the second one said if you give me any two real numbers x and y with x positive, then I can find a natural number. There exists a natural number n in n such that nx is greater than y. Alright, so with these two Archimedean properties, these two forms of Archimedean properties, we are going to prove some more results. Okay, so they are called applications of Archimedean property. So the first one is this theorem A. I'll be doing two under this. Okay, so this is the first one. This says given any x positive, if I give you any real number x which is positive, then there exists a natural number n such that 1 upon n will be less than x. Okay, so no matter what real number x you give me positive, no matter where on the real line, anywhere here, then for each such x, I'll be able to find one point here, a natural number such that 1 upon n will be less than x. I can always do this. Okay, so this is what the statement says. All right, so let's start. Now, if you compare the previous statement of Archimedean property, the second one, okay, if you look at the second one, that says given any xy in R with x positive, there exists a natural number n such that nx is bigger than y. Okay, so x is positive here in this one, and that's what our requirement is here in this theorem as well. Okay, x is positive, and proving the last inequality here, 1 by n is less than x, is same as proving 1 is less than nx, right? So this nx is same here, x is positive and n is a natural number. So if I pick up y equal to 1, okay, if I pick up y equal to 1 and I apply the second form of Archimedean property, then I'm done. That's what it says, right? So what I'll do, so before that I'll choose the point y to be equal to 1, which is a real number, and this x is already given to me. X is positive, is given. Okay, so by second form of Archimedean property, therefore by AP2, what I can say, there exists a natural number n such that nx is greater than y, right? So I can find a natural number. Therefore by this, there exists a natural number n such that n into x is bigger than y, but y is 1. That means nx is bigger than 1. And now if I multiply both the sides by 1 by x, because x is positive, 1 by x is well defined and is also positive. Okay, so x is positive, so 1 by x will also be positive. So if I multiply 1 by x on both the sides, so what will that give me? There exists a natural number n such that 1 upon n is less than x, right? Such that 1 upon n is strictly less than x, and that is what we wanted to prove. So given any positive real number x, I can find a natural number n such that 1 by n is less than x. A very important result which we will be using every now and then, okay, in the upcoming lectures. All right, so this is one of the properties that I wanted to prove. The second one is this. This says let x be greater than or equal to 0. So x is a non-negative real number. It can either be 0 or it has to be bigger than 0. It cannot be negative. Okay, so if I have a real number x which is greater than or equal to 0, then this real number x will be equal to 0 if and only if x is less than or equal to 1 by n for every natural number n. So this gives you an equivalent condition to show that a real number is 0. So whenever I want to show that a real number, some real number is 0, what I have to do? I have to show that it is less than or equal to 1 upon n for every natural number. That means it is less than 1. When n is equal to 1 here, I'll get 1. So it has to be less than 1. It has to be less than half. It has to be less than 1 by 3 and so on. It has to be less than every number of the form 1 by n for each natural number n. Okay, so it's a if and only if condition. So there are two sides for this, two implications, as you know from the statements chapter. So first we will assume that x is 0 and we will show that x is less than or equal to 1 by n for every n, and then the converse. Alright, so first I will assume that first part. So let x be equal to 0. Okay, let x be equal to 0. Then x is 0 and 1 by n will be a positive real number because n is a natural number, right? So x will be less than or equal to in fact strictly less than 1 by n for any n because n is positive. Now so x will be strictly less than 1 upon n for every natural number n, right? So x is strictly less than 1 by n here, so that is same as saying x is less than or equal to 1 by n for every n in n, because we know that x is strictly less than 1 by n. It is as good as saying x is less than or equal to 1 by n for each n, and that's what a second statement on the right hand side is. So what we did, we assumed that x is equal to 0 and we showed that x is less than or equal to 1 by n for every n. Okay, so one side is done. Conversely, I will assume that this part holds and then x equal to 0. Okay, so conversely, second part, converse part, assume that x is less than or equal to 1 upon n for every natural number. Okay, so the second statement I'm assuming, and what is the claim? I need to show that x is equal to 0. Okay, this is what I need to prove. We will go by contradiction here. I want to show that x is equal to 0. I'll assume that x is not equal to 0. Okay, so assume that x is not equal to 0. Okay, I'm going by contradiction, so that's a proof by contradiction. Okay, so that's a proof by contradiction. I hope you all are familiar with proofs by contradiction. Now x is not equal to 0. Now if you go back to the hypothesis and see x is greater than or equal to 0. Okay, so x has two choices, either it is 0 or it is positive, and now I'm assuming that it is not equal to 0. Okay, so that forces x to be strictly greater than 0 because it is not 0 and it cannot be negative by the hypothesis. So the only possibility for x is that it is strictly greater than 0, right? And if I look at the previous result which I did, it says if I take any positive real number x, then there exists a natural number n such that 1 upon n is less than x. So I can apply this result here. So because x is strictly positive by a, and this is the previous result I'm using, by a for x greater than 0. For this x greater than 0, there exists a natural number n such that 1 upon n is strictly less than x. So I found one natural number such that 1 upon n is strictly less than x. But what is my assumption here? I am assuming that for every natural number n, 1 upon n is bigger than or equal to x. And I have found one natural number n now. okay, such that 1 upon n is less than x. So that's a contradiction to our assumption. So I can give some name, let's say Roman number 1. So this is a contradiction to 1. That's a contradiction to 1. Why we are getting this contradiction? Because we assumed that x is not equal to 0. Okay. So our assumption is false and therefore x is equal to 0, and hence we have proved this result. Okay. So whenever I want to show that x is equal to 0, many times what we will be doing is we will be showing that x is less than or equal to 1 by n for every natural number n. So if you do this, you are showing that x is equal to 0. Fine. Another application of the Archimedean property is this result, which says z is neither bounded above nor below in R. Okay, so if you look at the set of integers, that is neither bounded above nor below in R. All right. So both these things we need to prove that it is not bounded above as well as below. So first we will show that to show that z is not bounded above in R. This is what we will show first. Okay, so again we'll go by contradiction. So we'll assume that z is bounded. So let if possible z be bounded above in R. Now z is bounded above in R, that means it is going to have an upper bound in R. So there must be a real number. So there exists a real number alpha in R such that alpha is an upper bound of z. That means alpha is bigger than every integer z. Okay, such that m is less than or equal to alpha for every integer m. Okay, so for all m in z, m must be less than or equal to alpha. So I have a real number alpha which is greater than or equal to all the integers. But we know that the set of natural numbers is a subset of the set of integers. So any upper bound if you take for z, that will be an upper bound for n also. Okay, and that will be a contradiction, because we have already shown that the set of natural numbers cannot be bounded above. It's not bounded above by Archimedean property, right? So because natural numbers is a subset of z, this implies n is less than or equal to alpha for every natural number alpha as well. It is true for every integer, and set of natural numbers is a subset of integers, right? So for every natural number n as well, n will be less than or equal to alpha for each n in n. That means n is bounded above in R, because we have found a upper bound alpha. So this is bounded above in R. That's a contradiction. Okay, so this is a contradiction to the first Archimedean property, the first form of Archimedean property, AP1. Why we are getting this contradiction? Because we assume that z is bounded above in R, and hence uh, z is not bounded above in R. Right? All right. So z is not bounded above in R. So one part is done. Z is not bounded above in R. Now we need to show that the set of integers z is not bounded below as well. Okay. So again we will go by the proof of contradiction. Okay. So I want to show that z is not bounded below in R, right? So to show that z is not bounded below in R. So this is a second step to complete the given statement. So again by contradiction, so let's assume that Z is bounded below. Let if possible Z be bounded below in R. So this is our assumption. I will call it uh, 2. Okay, let me call it 2, some number 2. So because Z is bounded below, it will have a lower bound. So there exists a real number beta in R such that beta is less than or equal to m for every integer m. So beta is a lower bound for m. So this is what we know from definition of the set being bounded below. Now if you note this, if I take any natural number n, okay, if I take any natural number n, then its negative will always be an integer no matter what that natural number n is, right? So no matter what this natural number n is, its negative is always going to be integer no matter what natural number n you pick up. And because minus n is an integer now and beta is a lower bound for the set of all integers, okay, that means minus n will be bigger than or equal to beta, or beta will be less than or equal to minus n, and this is for all natural numbers n. This n is arbitrary, okay, so let n belong to natural numbers, so this n is arbitrary. That means beta is less than or equal to minus n. Now if I multiply minus 1 on both the sides, what will I get? The inequality will reverse first of all, okay, so and I'll be getting minus beta is strictly bigger than n. This implies n is less than minus beta for every natural number n. That means we have shown that minus beta is bigger than every natural number, correct? That means minus beta is an upper bound of n, Again, that's a contradiction to the first form of Archimedean property, because the first form of Archimedean property says the set of natural numbers is not bounded above. Okay, so this is a contradiction to, this is another notation for contradiction. Okay, this is a contradiction to AP1, that's our first Archimedean property. And why we are getting this contradiction? Because we assume that the set of integers is bounded below, and hence Z is not bounded below in R. Not bounded below in R. Okay, so that's what we end up with. So the set of integers is neither bounded above nor below in R. Okay, now I'll state a definition. I missed this definition in the earlier videos. Okay, a set capital X is said to be bounded if it is both bounded above as well as below. If it is bounded above and below. Okay, so whenever I say a bounded set, okay, whenever I say a bounded set, it means that set is bounded above as well as below. All right. Now I have an exercise for you all. Now I defined the least upper bound property in the last video. Okay, so I want you all to think about the greatest lower bound property and try to frame greatest lower bound property like LUB property. Okay, so what you'll have to do is you'll frame the greatest lower bound property of R. Okay, greatest lower bound property of R. This is the first thing, and the second exercise I want to leave for you all is that assuming LUB property, you prove GLB property. In fact, you can prove that both are equivalent. Okay, prove that LUB property of R and GLB property of R are equivalent. Are equivalent. So you have to assume the LUB property of R and you have to show that GLB property of R works. It holds. Okay, GLB property of R, and similarly you have to assume the GLB property of R and you have to show that the LUB property of R works. Okay, so LUB property of R is equivalent to GLB property of R. Alright, so I want you all to try these two exercises. Okay, so I end this session with this, and these are my references. Thank you.